All right, welcome back to section 8.6 continued. This is part 2. We just finished off with example number 2, so let's get on to example number 3. We want to find a power series representation for the ratio x over the quantity x plus 1. So go ahead and please pause the video and see what you can come up with. It's good to play around with it a little bit before you start to see a solution, so that way you can figure out what you did right, what you did wrong, what you need to work on. So again, go ahead and pause it. All right, so this one, again, using algebra, we can come up with an answer to this in a relatively quick way. And we can do that by realizing that x over x plus 1 can be rewritten as x times the quantity 1 over 1 plus x. So I just factoring the x out, and then I'm rewriting the denominator as 1 plus x instead of x plus 1. Now recall that 1 over 1 plus x has the power series expansion of 1 minus x plus x squared minus x cubed and so forth. So we can write this as x times 1 minus x plus x squared minus x cubed plus x to the fourth minus plus negative 1 to the n, x to the n, plus And so now all we have to do is distribute, and we get x minus x squared plus x cubed minus x to the fourth plus x to the fifth minus plus negative 1 to the n, x to the n plus 1 plus Or in summation notation, we would still get the sum from n equals 0 to infinity, negative 1 to the n, and here we'll have x to the n plus 1. And so there's our power series representation for x over the quantity x plus 1. And all we did was some algebraic manipulation on the given function and related it to a power series that we already know. And again, in this section here, that's primarily what we're going to be doing until we learn the more general method in section 8.7. We should still talk about the interval of convergence here to make sure that we know for what values of x this relationship is valid. And keep in mind that if we look up at what's happening up here to this series term by term, we notice we're just multiplying by negative x each time, so we still get the magnitude of negative x has to be less than 1, or in other words, the magnitude of x has to be less than 1. So we're still looking on the open interval negative 1 to 1 by our conditions from the geometric series properties. All right, let's take a look at another example. Actually, I stand corrected. Not another example. Let's look at some other properties and theorems related to power series expansions. So let's get to that. All right. So as I said earlier in part 1 of this lecture and in section 8.5, that a power series is a function. And it's a function whose domain is the interval of convergence for that series. And so what we're going to do in this theorem that you're looking at right now is we're going to now be allowed to use our calculus skills in trying to determine power series for different functions. So here's our theorem. If a power series, which is the sum of c sub n times the quantity x minus a to the n, note this is the more general power series centered at a rather than centered just at 0, has a radius of convergence r greater than 0. So in other words, it's not convergent only at the single point. If r equals 0, then it's only convergent at the center, and that's it. So we're now saying it can't be convergent only at the center. It's got to have some other values of x for which the series converges. Then the function f defined by, well, f of x equals this power series, c sub 0 plus c sub 1 times x minus a to the first power, plus c sub 2 times x minus a to the second power, and so forth. I didn't put the nth term on there because it's going to be hard to squeeze it in and then still put the plus ... afterwards, so I just left it like that. But this is the power series. Is differentiable, so we're told as long as we have a radius that's greater than 0, we know the power series is differentiable. Recall that if a function is differentiable, it is therefore continuous. The converse is false. Being continuous does not imply differentiability, but being differentiable does imply continuous. So this function is is differentiable and therefore continuous on the interval a minus r to a plus r. Open interval, because we never have differentiability at the endpoints. And remember, the center is a, and r tells us how far to move away from the center. So a minus r moves us r units to the left of a on the number line, and a plus r is moving a units to the right of a. R units to the right of a on the number line. And f prime of x equals. Now we're going to work this out together. So let's look back here at f of x for a moment. We're going to take the derivative just term by term over here. So the derivative of a constant, of course, is, everybody should get that 0 right there. So I'm not even going to write it down. The derivative of c1 times x minus a is, well, hopefully we're all just yelled at c sub 1. The derivative of c sub 2 times the quantity x minus a squared, hopefully we're all saying 2 times c sub 2 times x minus a, plus, now I know the third term isn't written down right now, but it would be c sub 3 times the quantity x minus a cubed. And so the constant c sub 3 is still going to be there in the derivative. X minus a, its in derivative of the inner function is 1, as it was in the other cases, so it doesn't really affect anything. So by the power rule, hopefully you're imagining we'll have a 3c sub 3 times x minus a squared plus, well, let's get to the dot dot dot, plus the nth term, of course, is c sub n times the quantity x minus a to the nth power. So the derivative would be n times c sub n times the quantity x minus a to the n minus 1 power plus dot dot dot. So all we're saying is that we have a differentiable function here. Power series are differentiable functions provided they converge on some interval and not just at the single point that is the center. And to find the derivative, we just take the derivative term by term. Take the derivative of the first term, and then add to it the derivative of the second term, and then add to it the derivative of the third term, and so forth, indefinitely. Okay. The second part of this theorem is in regards to the integral. The antiderivative of f of x dx, well, we're going to do this the same way. We're going to take antiderivatives term by term. Okay. Now, of course, we're taking an indefinite integral, so we need some constant. So I'm going to put a capital C first, because all of our indefinite integrals are families of curves, and we end up with our whatever our antiderivative is plus c. So let's get rid of that issue now. Let's get the plus c on there right away, and because we're going to have an infinite number of terms, and I just don't want to have that hooked on to the end. So now going back to f, right over here. I know it's kind of lost in the green scribble that I put on here. The antiderivative of c is just supposed to be c times x. We're going to call it, though, c sub 0 times x, but we're going to call it c sub 0 times x minus a. And the reason why we want to do that is because we want every term to have the same pattern to it. So I want every term to have that factor x minus a. That's not already just a constant term. And you might ask, well, how am I allowed to do that? Am I really violating some aspect of the mathematics here just to make it, force it to look like it should, like everything else? And the answer to that is no, because the constant that we have here, this capital C, that constant balances out this shift of making c sub 0 times the quantity x minus a instead of just c sub 0 times x. Because in reality, if I distribute the c sub 0 to x and the a, I get c sub 0x minus c sub 0a. And the c sub 0a is some constant. Whatever it is, it's going to collect with the capital C and have, as long as we've done the other calculations correctly, it'll be the correct quantity because this constant C is what's balancing any other constants that are there. So although that may seem a little bit odd, I hope it's not too difficult to comprehend. In other words, capital C is a constant, C sub 0 times A is a constant, and this capital C is balancing out the extra little constant that's being contributed by the C sub 0 times A. Let's go to the next term. We have C sub 1 times x minus A. So we're taking the antiderivative of the x minus A part. C sub 1 is a constant, so we use the constant multiple rule. So x minus A, if we did a u substitution, u letting u equal x minus A, du is just dx. And so really the antiderivative of this is just going to be the x minus A squared over 2. Then, of course, times c sub 1. And so I'm going to write it as plus c sub 1 times x minus A squared, that quantity squared, over 2. If you're not quite sure that that worked, then just take the derivative of the term I just wrote down and make sure that it all cancels back down to be c sub 1 times the quantity x minus A. And you'll see that it works. You'll notice that if we can do this for one more term, we'll get c sub 2 times x minus A. It was squared before, so add 1 to the exponent to get cubed and divide by that new exponent to get a 3 in the denominator. And then we continue with this pattern. Dot, 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 plus, dot, 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 plus. We're eventually going to get to c sub n. We'll have x minus A quantity to the nth power, and we're going to have to add 1 to that n, divide by the new exponent, n plus 1, and we get our plus dot, dot, dot. Again, just like in the first part where we took the derivative term by term, here we're taking the antiderivative term by term with a couple minor little tweaks. We have our constant integration, which we start with so that we don't accidentally forget it later and actually have to hook it on after a plus dot, dot, dot. It just looks a little bit better. But again, all we're doing is, we're shifting the c sub 0 term to be at the center, x minus A, instead of just times x. But we're just integrating term by term, taking the antiderivative term by term, and that's how we would work with our power series F. One last little sentence here. The radii of convergence of the power series in parts 1 and 2. I was supposed to switch colors and I forgot. Are both capital R. So in other words, in taking the derivative of a power series with radius r, or taking the antiderivative of a power series with radius r, those derivatives or antiderivatives still have the same radius as the original function or original power series. Doesn't change anything. So example 4 says to find a power series representation for the function -1 divided by the quantity 1 plus x squared. So pause the video, go give it a shot, see if you can use that last theorem to come up with some sort of result. Alright, so hopefully we had some success, or at least made some sort of progress to understand better what we need to do. You may notice something about this expression or function that we're trying to find the power series for. It's related to one of the power series that we already know. If we were to take the derivative with respect to x of 1 over 1 plus x, we would get this -1 over 1 plus x quantity squared. So, in other words, I know this function is directly related through differentiation to one of the power series I already know. I know a power series for 1 over 1 plus x. So, I could use that in order to generate the power series for this function by taking a derivative. So we know 1 over 1 plus x is equal to 1 minus x plus x squared minus x cubed plus x to the fourth minus dot 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 plus negative 1 to the n, x to the n plus dot dot dot. One that we have to know, one that you have to memorize. And so we know 1 over 1 minus x, we know 1 over 1 plus x. Directly related to each other, and one can be used to get to the other. We have to know both of those. And so, from here, let's go ahead and differentiate both sides. Okay, so we'll just abbreviate it here. So by differentiating the left-hand side, we get negative 1 over the quantity 1 plus x squared, as we saw on the previous page, which is the function that I'm trying to represent with the power series. And now all I have to do is differentiate term by term the right-hand side. The derivative of 1, 0. Derivative of negative x, negative 1. Plus 2x minus 3x squared plus 4x cubed minus dot 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 plus negative 1 to the n x to the n minus 1 plus dot dot dot. Now I'm going to back out of this a little bit so see if I can make this a little bit closer together. So we had 3x squared plus 4x cubed minus dot 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 plus, again, negative 1 to the n x to the n minus 1 plus dot dot dot. Now I can fit it better on the screen. And so here we go. This is our power series representation. We want to write this in maybe summation notation for practice. This would be the sum of, well, let me write the expression down here. It's this last expression that we had, negative 1 to the n times n x to the n minus 1. And so here, my indices, I know the top indices, the upper bound is going to head off to infinity. Do I start the lower indices by plugging in 0 or what? Well, hopefully you could see I'd have to plug in 1 in order to get the first term negative 1. Because negative 1 to the first power would be negative 1. N as 1 is 1. And then x to the 1 minus 1, or x to 0 is 1. So this all becomes negative 1 times 1 times 1, which is still negative 1. And if you plug in 2 and 3 and 4, you'll see the rest of the terms develop as well. Again, you should always think, for what values of x is this relationship true? In other words, what is the interval of convergence? And so I'm sorry, hold on real quick. From our theorem, the interval of convergence is still the same. Well, it's still the open interval from before, because remember from our theorem that the radii of convergence are still the same, still both are. And so if I go back to this a little further, it's differentiable over the interval from a minus r to a plus r. And so getting back to this over here, the center of this power series, I hope we recognize, since we don't have an x minus a explicitly there, is 0. And so if my radius of convergence for the original function is 1, the radius of convergence is 1 for this one, and so the interval of convergence is going to be from negative 1 to 1. Excuse me. I'm spelling interval wrong. The interval of convergence is going to be from negative 1 to 1. Let me repeat that really quickly. The original function has an interval of convergence, negative 1 to 1, has a radius of convergence of 1. When I take the derivative of it, the power series of the function, the interval of convergence and the radius of convergence essentially don't change. The only way they could change is that in the interval of convergence, if the endpoints were included, now they wouldn't be included in the derivative, because a function is not differentiable at the endpoints. And so, even though this one here that we're dealing with, it did include the endpoints anyways, but just in case other examples did. So our radius of convergence was 1, our interval of convergence was negative 1 to 1, so when taking the derivative, we get the same interval of convergence. It'll always be that open interval from which the original function was convergent upon. All right. Let's see here. Example number 5. All right, so example 5a. Find a power series representation for the natural log of the absolute value of the quantity x plus 1 and its radius of convergence. So go ahead and pause the video. Give it a shot. So hopefully we had some success. Let's see how we can make a connection here. Notice that if we were to take the antiderivative of one of our known functions, 1 over 1 plus x dx, we would get the natural log of the absolute value of x plus 1 or 1 plus x, that order doesn't matter, of course, plus a constant. And so here's our connection. Again, using a power series that a function we already know the power series of, or for, and connecting it to the current function that we're trying to find the power series for, we can go ahead and use some calculus to make that connection and now have a plan for going and solving for this power series. In other words, once I know the power series for this 1 over 1 plus x, I can integrate the series term by term to get the power series for the function that I'm working for or looking for. So 1 over 1 plus x, as we know, is 1 minus x plus x squared minus x cubed plus x to the 4th minus ... plus negative 1 to the n, x to the n plus ... All right, so now let's integrate both sides. And so for integrating both sides, we're going to get over here the natural log of the absolute value of x plus 1. I am going to commute that to the order it looks like in the expression they gave us. Not necessary, but I'm just going to. And then over here, of course, we're going to have our constant of integration c. The antiderivative of x, of 1 is just x. And then the antiderivative of x is 1/2 x squared, so we have a minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the 4th plus ... let's see, plus the nth term, we will still have this negative 1 to the n, but now we're going to have x to the power of n plus 1 over n plus 1 plus ... All right, so sometimes we can figure out what the center is. Knowing the center, we can figure out what the constant is. So we know that the center of this series is 0, because notice our expressions all have x instead of x minus a for some value a. Or if you want to get technical, x minus 0 is sitting there, even though we don't see the minus 0 part. So if we plug in the center, we can help figure out what that constant is. So if we have, if we let x equal 0, then the natural log of the absolute value of 0 plus 1, well, we should know that that's just the natural log of 1, and we should know that the natural log of 1 is 0. And so now plugging 0 into the power series, I still get that constant, but every other term is just 0 to some power times some constant, which is going to be 0. So that tells me that c is 0, so that my power series representation is going to be the natural log of the absolute value of the quantity x plus 1 is equal to just x minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the 4th plus ... plus negative 1 to the n, x to the n plus 1 over n plus 1 plus ... All right. Let me give you a part B. So let's use example B. That should be 5B. Use part A to approximate the natural log of the quantity 1.1, correct to 4 decimal places. I'll give you a hint. We only have one technique for doing this. Okay, there's your hint. And I will give you the answer that you should get. And the natural log of 1.1, according to our approximation, correct to 4 decimal places, using what you're supposed to use, is going to be 0.0953. So if you don't get that, well, then you got some more work to do and more studying to do. So work to get that answer. On Friday when we go over this, we'll finish up these notes. We're awfully close to the end of section 8.6's notes, but I'm going to show you some graphs. We'll do a few more examples, clarify any, hopefully few, but any misconceptions that we might have. All right, go study.